To create more realistic depictions of three-dimensional scenes on a canvas, mathematicians and artists began to study projection. Artists summarized the fundamental principles of projective geometry, leading to the development of perspective drawing. Inspired by the transformations and invariants found in the projection process, group theory and symmetry were introduced into geometry by mathematicians and became the foundation of modern mathematics. The same ideas also influenced the content and direction of modern physics research. It all began with the study of projection. This video will guide you through the basic concepts of projection, explore its applications in art, and reveal its impact on modern mathematics and physics. Whether in photography, painting, or computer screen displays, the essence is to realistically represent three-dimensional objects on a two-dimensional plane. Projecting a three-dimensional object onto a two-dimensional plane, or more precisely, transforming geometric shapes from three-dimensional space to the two-dimensional plane, is known as projection. There are two fundamental concepts in the projection process: the projection plane and the projection center. The projection plane is straightforward. It is the plane where the projection result is displayed. The projection center is a fixed point in space during the projection process. Connecting a point on the original three-dimensional object to the projection center, the intersection with the projection plane forms the corresponding projection point. The collection of projection points for every point on the three-dimensional object forms its projected image on the two-dimensional plane. In the process of painting, the artist's eye acts as the projection center, and the projection plane is the artist's canvas. In photography and filming, the projection center is the position of the lens. The lens captures light rays emitted by the object, which pass through the projection plane and converge at the projection center, forming an image on the film. By connecting points to the projection center and projecting them onto the plane, this forms a projection transformation. Through studying the geometric properties of the projection process, artists created more realistic artworks, and mathematicians developed a new discipline: projective geometry. The Renaissance marked the beginning of a new era in human history, bringing forth many great artists such as Masaccio, Leonardo da Vinci, Uccello, Raphael, and Michelangelo. Thanks to their study of the geometric properties of projection, they created numerous vivid and realistic paintings. Their works were filled with the application of perspective techniques. Let's explore some fundamental techniques of perspective through a few examples. This is Leonardo da Vinci's The Last Supper. All lines in space that are perpendicular to the canvas converge at a single point. This is one of the basic techniques of perspective drawing, known as one-point perspective. The point where parallel lines appear to converge on the projection plane is called the vanishing point. If we observe these lines in three-dimensional space, we can clearly see that they are parallel. But on the canvas, these lines converge at their vanishing point. This is Raphael's The School of Athens. In this work, one-point perspective is also employed. All lines in space that are perpendicular to the canvas converge at a single vanishing point on the painting. Even if it is not directly drawn, connecting corresponding points reveals hidden lines perpendicular to the canvas that also converge at this point. This is the essence of one-point perspective. Sometimes, to depict two sets of parallel lines pointing in different directions, we use two-point perspective. This is Paris Street, Rainy Day, by the French artist Gustave Caillebotte. In the distance, the parallel window frames on both sides of the building converge at two different vanishing points on the canvas. If we observe these lines in three-dimensional space, we can clearly see two sets of horizontal parallel lines pointing in different directions. But on the canvas, these lines converge at two different vanishing points. Both of these points lie on the horizon line in the painting. Each set of parallel lines in three-dimensional space converges at its own vanishing point on the canvas. If the set of parallel lines is also parallel to the ground, its vanishing point will be on the horizon line. A curved road without any elevation illustrates this principle as well. Each pair of parallel edges along the road converges at a point on the canvas, and these points all lie on the horizon line. In addition to managing parallel lines and their vanishing points, perspective techniques encompass other methods such as representing objects as appearing larger when closer and smaller when farther away, or brighter when near and dimmer when distant. Renaissance artists, through their study of projection geometry, mastered these techniques and created vivid, lifelike artworks that marked a significant evolution in the history of art. The study of the geometric properties of projection began as an applied branch of traditional geometry. However, projective geometry, in the history of mathematics and science as a whole, is far more than just an applied science. It subtly changed how mathematicians viewed geometry. Geometry shifted its focus from studying the characteristics of objects in space to treating transformations as a primary subject of study. In 1872, the German mathematician Felix Klein published the Erlangen program, a milestone in the history of science that ushered in the era of modern mathematics and physics. In his program, Klein proposed a method for classifying different branches of geometry based on the study of invariants under various transformations. This concept established a unifying framework for projective geometry, affine geometry, Euclidean geometry, and hyperbolic geometry. Consequently, the theory of transformation groups was brought to the forefront of geometry, solidifying the foundational role of group theory in modern mathematics. The Erlangen program also influenced the further development of geometry, providing a framework that shaped the positioning and research focus of later fields such as Riemannian geometry and topology. The Erlangen program also had a profound impact on modern physics. The study of transformation groups, particularly the investigation of invariants, or symmetries, and deriving conservation from symmetry based on Noether's theorem, became a core framework for understanding fundamental interactions and natural laws in physics. The formulation and development of theories such as special relativity, general relativity, gauge field theory, the standard model of particle physics, and string theory have all been influenced and guided by this idea. It is no exaggeration to say that the Erlangen program laid the foundation for modern mathematics and physics. It all began with projection. It was the study of projective geometry and its transformations that inspired the creation of the Erlangen program.